In this example, we're given two signals, x of t as well as y of t, and we're asked to express x of t mathematically and then to express y of t as a combination of shifting and scaling of x of t. Or, in other words, to find the values of a and b for which y of t is equal to x of at plus b. Now, let's focus on part A. In order to obtain a mathematical expression for x of t, we can multiply the signal e to the power negative t, which I'll sketch over here. So we multiply that signal by another signal that looks something like this. This is simply a rectangular pulse of amplitude 1 for values of time between 0 and 2. And this rectangular pulse can be described mathematically quite easily with the help of the unit step function. This is simply the unit step function minus another step unit function delayed by 2 units of time. So x of t can be obtained by multiplying these two signals, which gives us e to the power negative t times the unit step function minus another unit step function delayed by 2 units of time. Now, let's work on part B. In order to express y of t as a combination of shifting and scaling of x of t, it makes sense to split this problem into two sub-problems. We see that y of t is a time-compressed version of x of t that is also shifted to the right by a certain amount of time. So if we focus on one transformation at a time, we could create an intermediary signal, which I'll call phi of t, which is just a time-compressed version of x of t. And I'll sketch that over here. It will look something like this. Now, it is quite or relatively easy to find the relationship between phi of t and x of t. We know that phi of t is simply a time-compressed version of x of t by a factor 2. Mathematically, this can be written as phi of t is equal to x of 2t. Similarly, it is quite easy to find a mathematical relationship between y of t and phi of t. Y of t is simply the signal phi of t that's been time delayed by 3 units of time. And mathematically speaking, we can write y of t is equal to phi of t minus 3. Now, if we want to express y of t as a combination of shifting and scaling of x of t, we need to combine these two expressions. In order to do that, since y of t is equal to phi of t minus 3, we simply need to substitute t here by t minus 3. Then we'll substitute t here by t minus 3. So, to summarize, y of t, which is equal to phi of t minus 3, and that's equal to x of 2 times t minus 3, or simply x of 2t minus 6. And let me write that over here. Y of t is equal to x of 2t minus 6. Now, it would be reassuring if we could make sure that this relationship holds for specific values of time. For example, we know that the amplitude of y of t at time t is equal to 3 should be the same as the amplitude of x of t at time t is equal to 0. Similarly, we know that the amplitude of y of t at time t is equal to 4 should be the same as the amplitude of x of t at time t is equal to 2. In our mathematical expression, if we try y of 3, then that would be equal to x of 2 times 3 minus 6, or x of 0, which is correct. For y of 4, then that would be equal to x of 2 times 4 minus 6, or x is x of 2, which is also correct. Now, if we were asked to find an expression for y of t that is a pure function of time, then we would simply need to substitute t here by 2t minus 6. So we could also write y of t is equal to e to the power negative 2t minus 6 times the unit step function with 2t minus 6 as a parameter minus another unit step function with 2t minus 8 as a parameter. And this expression and this expression for y of t are equivalent.